Okay, hello, welcome everyone to today's seminar. We're very happy today to have Matthew Dodelson from Kavli or IPMU, who's going to tell us about singularities of thermal correlators at strong coupling. So Matthew, the floor is yours.
Okay, well, thanks for the introduction and for the invitation. So this work is based on 2010-09-734 with Hiroshi Ooguri from last year. And it's on singularities of thermal correlation functions at strong coupling. So here's the basic overview. I'll start out by motivating the result using something called the bulk points singularity. This is a singularity in correlation functions in vacuum ADS-CFT. And then I'll move on to thermal ADS-CFT. I'll consider the two-point function. And I'll study the singularities of the two-point function by looking at the ADS black hole. The main part of my talk is sections 3 through 5. In these sections, I'll show that this singularity in the two-point function is actually resolved in string theory. And I'll conclude with some more general black holes and a summary and future directions. So that's the basic outline. So let's start with the bulk point singularity. The question I'm interested in is what kinds of singularities can arise in correlation functions in conformal field theories. So in ordinary quantum field theory, we have the scattering matrix, and we can study singularities of the scattering matrix, and these correspond to on-shell physical states, which are obviously a fundamental part of the theory. In a conformal field theory, we don't have the scattering matrix, but we have position space correlation functions. And we can ask what kinds of singularities are allowed in these correlation functions. So in Euclidean signature, there's not many allowed. All that's allowed is the OP's singularity. So namely, two operators can get very close to each other. And here, O of x1 and O of x2 are two operators, and x1 is approaching x2. And in this limit, the correlation function is a power law that diverges with power determined by the scaling dimension of the operators. So that's not that interesting because it's completely determined by the scaling dimension of the operator, along with conformal invariance. But in Lorentzian signature, things get more interesting because we can have singularities that are not at coincident points. So meaning we have 2 points that are not on top of each other, and yet the correlation function is still singular. So the obvious example would be the light cone singularity. If we have two operators that are light-like separated, then the correlation function is singular. A slightly more non-trivial example is called the Landau singularity. And this occurs when we can draw a Feynman diagram that has only light-like lines in position space. So there are some edges and some vertices, and all the edges are light rays. So in that configuration, if it exists, then the correlation function is in fact singular. And perturbatively, you can show that there are no more singularities. All the singularities are light cone singularities or Landau singularities. And also in 1 + 1 dimensions, you can show that there are no additional singularities. But in higher dimensions or non-perturbatively, there could be more interesting singularities, and we want to see if they exist or not. So one regime that we could look for them in is the holographic regime, namely large n and large lambda. In this regime, what happens is that there are now Landau diagrams in the bulk. So that's drawn down here. This is the ADS3 cylinder, 4 points x1, x2, x3, and x4 on the bulk. And we have a point P, 4 points x1, x2, x3, x4 on the boundary, and we have a point P in the bulk, and they're all connected via light rays. And so this is now a Landau diagram in the bulk, and this leads to singularities in the boundary correlation functions. So these are called bulk point singularities, first derived by Gary, Giddings, and Penrose. So here's an example. In this ADS3 context, the correlation function diverges as a power law. With this power, here's Z and Z bar are the conformal cross ratios corresponding to these points. And so the bulk point singularity is at Z equals Z bar. So in fact, you could show that in general, for these kinematics, there's no Landau diagram on the boundary, only in the bulk. So it seems like this is really a new singularity, and it's not visible in perturbation theory. However, we have to remember that field theory, a local field theory in the bulk is only okay if we take the strict limit where the 't Hooft coupling and n go to infinity. So we should really keep them finite, and then consider the theory at that finite value. And if we keep lambda finite and sum up all the stringy corrections, what you find is that the singularity is actually smoothed out by the expansion of the world sheet. So that was shown by Maldasenis and Duffin and Zhiboedov. And so really this singularity is an artifact of the infinite lambda limit.
Excuse me, Matthew.
Yes. Yes.
I want to ask you that in the figure you have shown, what are Z and Z bar?
Yeah, so it's the conformal cross ratio of these points x1, x2, x3, and x4. So it's I guess the usual thing that we're used to, x1 minus x3 times x2 minus x4 over x1 minus x4 times x2 minus x3. I don't remember the exact thing, but
okay, it's the cross ratio.
Yeah. So, but the way to think about it physically is that Z minus Z bar equals 0 when the time separation between the initial 2 points and the final 2 points is equal to pi. And the reason is because it takes a time pi for the geodesic to get back out to the boundary. So this kinematic limit is really that the change in time is equal to pi. So, yeah.
Okay, so this one is not really a null-like singularity. So that's why you call it a new singularity.
So all these lines are null, but the points on the boundary are not connected by null rays. They're only connected to this bulk point P by a null ray. So it's a Landau diagram, but it's not a light cone singularity.
Okay, I see. Thanks.
Sure. So in general, in higher dimensions, you can show that, or we showed that the only singularities with correlation functions in a holographic theory occur when there's a boundary Landau diagram. We can try to extend this result to other states. So for instance, we can take a thermal ensemble and we can see and we can analyze the correlation functions in this thermal state. So at finite temperature, you can actually get interesting results even at 2 points, because conformal invariance is broken, so you can just look at the 2-point function. So that's what I'll do in this talk. And so we're interested in the singularities of this function of T phi of 0, 0 at finite temperature beta. So here phi is the angular coordinate on the sphere, and T is the time coordinate. So let's take a couple of limits of this correlation function. So the first limit is the infinite volume limit in 1 + 1 dimensions. In this case, you can conformally map to the plane. And so the only singularity is at t equals plus or minus phi, which is the ordinary light cone singularity. Also in free field theory, you can just compute this thing. And again, you find new singularities.
Sorry, can I have a question, please?
Yeah, sure.
Yeah, so what kind of correlation function you're interested in? It's going to be a real-time correlation function, right?
Yes.
So you're interested in time ordered, or?
Yeah, let's take this time to be greater than 0. Yeah.
Okay.
But we're doing it in position space, not in the momentum space. So it's a little bit simpler. The questions of the ordering. Yeah.
Okay. Thanks.
Yeah. Sure. So the third example where this simplifies is actually in a rational conformal field theory in 1 + 1 dimensions. In that case, you can show that the conformal blocks are holomorphic, and so there can't be singularities except on the ordinary light cone, which is t equals plus or minus phi. So so those are 3 examples, but we want to understand the more general case. And in the rest of this talk, I'll discuss the holographic limit of this correlation function. And we want to ask if there are new singularities, and if so, is the situation like the bulk point singularity, which would mean that they are actually resolved at finite string coupling, or sorry, at finite string scale, lambda. So that's the motivation, and now we can move on to the talk. Are there any questions about this so far? Okay, so let's talk about the ADS black hole. So we're interested in this obviously because this is dual to a thermal state on the boundary. So we want to know where the singularities of the boundary 2-point function are. And a good diagnostic for this is to just look for the kinematics where 2 boundary points are separated by a null geodesic. And so this was first analyzed by Hibeni, Liu, and Rangamani in 2006. And so what this means is that we should study null geodesics in the ADS black hole. So here I wrote down the metric. F of r is this function r squared plus 1 minus m over r to the d minus 2. M is the mass of the black hole. T is the time coordinate, r is the radial coordinate, and then we have some spherical coordinates. So to compute the null trajectories, we can use the fact that there are 2 conserved quantities, namely E and L, the energy and the angular momentum. And if we have a null geodesic, then it's parameterized by E over L. Only the ratio matters. The radial motion is determined by this equation, r dot squared equals E squared minus 2v. Here v looks like a potential for a particle in 1 dimension. So I drew this potential here, and we see that it has this feature that it has a maximum at a certain radius, and this is called the photon sphere. It's the radius. It's the closest radius a null geodesic can get to the black hole and still escape. So the photon sphere is at the maximum of this potential. And this is the qualitative plot for any d that's greater than 2. For d equals 2, there's no maximum. And so what this means is that for any d greater than 2, there are geodesics that come in from infinity and roll up the potential and escape back out to infinity. And these give singularities in the 2-point function. So let's try to understand the schematic behavior of these geodesics using the potential. So the first case would be a geodesic that just stays at the boundary. It just winds around, and it can connect these 2 points, x1 and x2. Second, there's a geodesic that stays far away from the black hole, so that the space-time is approximately anti-de Sitter space. And these geodesics have traverse an angle which is approximately pi, because they're approximately geodesics in ADS. So that looks like this. And then finally, there are geodesics that come in from infinity and roll up the potential and almost get there and roll back down. And what that means in this real space is that they wrap the photon sphere many times. So it comes in, it spends a long time near the photon sphere, and it goes back out to infinity. So that would be a few kinds of geodesics that connect 2 points, and each one of them leads to a singularity in the 2-point function. So we can compute the location of these singularities by just solving the geodesic equations. So we have some differential equations that we just need to integrate. Here, r plus and r minus are the 2 zeros of r dot. So here, r dot is a quartic equation in 1 over r. Oh, sorry, and here I'm in d equals 4. So I'm in ADS 5.
So it's hard since there is no bulk vertex like you had in the 4-point example. What is the source of the singularity here? There is no bulk lambda diagram you're drawing, right? Or
yeah, right. So this is literally just a singularity on the light cone. So yeah.
Okay. Yeah. Mm-hmm.
So it's actually much simpler than a Landau diagram. Although in a thermal state, a 2-point function is kind of like a 4-point function, because they have the same number of kinematics. So the analogy is a little bit better than just just that.
Thanks.
Okay, good. So yeah, so I forgot to mention I'm in d equals. I'm a little confused. Sorry. There's a typo here that propagated from a previous talk. This should be r to the d in the denominator, and then in d equals 4, which is what I'm specializing to. This is a quartic equation in 1 over r, and these r plus and r minuses are the 2 solutions to the quartic equation. R plus is outside of the horizon and R minus is inside of the horizon. So R plus is the real turning point of this geodesic. And we can just do these integrals. There's some elliptic function k, and that's the solution. And finally, after reaching the boundary, the geodesic can bounce back into the bulk, and this leads to infinitely more branches of the singularity, just like in vacuum ADS. So the full picture is like this. So here we have the angular coordinate phi and the time coordinate t. Phi is identified with 5 plus 2 pi. This red line is the ordinary boundary singularity. So that would be this first class of geodesics here, a geodesic that stays at the boundary. And then we have these blue lines. So the first blue line is a geodesic that comes in from the boundary, and it escapes back out to the boundary, and it doesn't bounce off. And then these higher blue lines correspond to multiple bouncings off the boundary. So yeah. So to understand these better, let's take some limits. In the very early time, yeah.
Can I have one more question? So the 2-point function of we are on a circle. So is it essential that we are on a circle, or like that's not essential? Because what I would say is that like the 2-point function on the plane at on the line at non-zero temperature is fixed by conformal symmetry, right? So I was just wondering if these features persist there, or you have to be on a circle to see them.
Yeah, it has to be finite volume, because otherwise the geodesics can't escape back out to the boundary. So if we took what's it called, a black brain, I think, where something that's dual to ADS-CFT at infinite volume, then these singularities go away.
I see.
So
Thanks.
And we can see that because this blue line, this new singularity, starts appearing at phi equals pi. And that corresponds to a geodesic that's very far away from the black hole. But then this line continues, and at very late times, it approaches a straight line. So we'll see why in a second. So in the late time limit, as I said before, it wraps around the photon sphere many times. So the velocity of the geodesic, the slope of this line is approximately the velocity of the geodesic at the photon sphere, and this is the velocity, and that's therefore the slope of this line. Very good. So it's a little simpler to draw it if we identify phi with phi plus 2 pi, because then we see that everything's in fact inside of the light cone on the boundary. There's no violation of causality here. But now we see that there's a complicated structure of caustic points. There are points where two null geodesics intersect, for instance here or here. And so there's a pretty complicated structure of singularities in this theory. Okay, so that tells us the positions of the correlator, and now we want to understand the form of the correlator as we approach the singularity. So to do this, we'll take the limit where the 2 points are connected by a slightly space-like geodesic, almost null, and then take the null limit. So the geodesic approximation in that limit gives that the correlation function is e to the minus m times the renormalized length, where the renormalized length is the length minus log of the cutoff, and we find minus log v squared minus l squared. So that tells us the correlation function, but we really want E and L, not E and L in terms of the boundary variables delta phi and delta t, and we can use these equations to make that change of variables. And what you find is that at very late times, for instance, the correlation function diverges with the same power as in vacuum ADS-CFT, except for this extra velocity of the photon sphere there. So it's a simple parallel behavior, but it has a slightly different dependence here. Okay, so that completes this effective field theory computation.
Question?
Yes.
Can one see here that this 2-point function respects the KMS symmetry?
Yeah, so that is that the periodicity in Euclidean time?
Yeah.
Yeah, you can, but you have to be more careful with the geodesics because there's this old analysis by the group at Stanford. So you have to use the geodesic approximation, and you have to track it as they go from one side of the black hole to the other, and it gets a little more complicated. But yeah, you can see it, but it gets more complicated.
Okay, so because from your formula, it's not so obvious that it's true.
Yeah. So this only applies in the Lorentzian regime for sure. It should not be taken to hold in Euclidean time also. So as you take t to the other side, there's going to be other saddle point contributions to the world line path integral, and you have to take those into account also.
Okay.
But luckily, I don't have to because I'm only interested in one-sided correlators in this talk. Great. Any other questions on this setup here? Okay. So now let's turn to string theory. So I showed you how there can be new singularities in the thermal 2-point function at strong coupling and large n, and I also claimed that they're not there in free field theory. So what that suggests is that they're an artifact of the infinite coupling limit, and at any finite coupling, they disappear. So that would be the case for the bulk point singularity, and we want to see if it's true here too. Unfortunately, it's not as clear here how to address this question, because how do we do string theory in the black hole? It's a strongly interacting sigma model on the worldsheet. But fortunately, we don't need the full theory. We just need it very close to the null of geodesic, because that's where all the physics is taking place. So in other words, we need some way to zoom in on a given null geodesic, and this is called taking the Penrose limit. So the way this works is if you have a metric G and a null geodesic gamma, then the Penrose metric is given by this metric. Here, A is called the plane wave matrix. It's the projection of the curvature onto the geodesic gamma, and U is a coordinate that's tangent to gamma. Sorry, and V is another null coordinate, and here these x's are called the transverse coordinates. So this describes the geometry that's very close to the null geodesic, and it's all that I'll need in this talk. So this the physical interpretation of this plane wave matrix is that it captured all the effects of tidal forces on extended objects that are propagating near the null geodesic, and luckily for us, that's exactly what we need, because we have strings that are propagating in the gravitational background, and we want to see how these extended strings are affected by the tidal forces in this geometry. So now let's review a couple of very simple examples. So if we have a maximally symmetric spacetime like ADS or flat space, then this plane wave matrix is 0. So that means that there's no tidal force near a null geodesic in ADS or in flat space. So that's the most trivial case. The second example would be what's called the plane wave or the BMN limit of ADS CFT. In this case, we consider a null geodesic in S5 on the equator of S5 for the spacetime ADS5 times S5. And in this case, what you find is that the plane wave matrix is actually a constant. So that's a more simple form of the metric than usual. So those are two simple examples, and now we want to study the theory in general. So for point particles, we have this world line Lagrangian. So I just plugged in the metric into the action. So it still looks pretty complicated because there's this complex interacting term here. But in fact, it's a completely solvable theory because we can fix the light cone gauge U equals PV times tau. And in this gauge, we see that everything is completely quadratic in the fields, although it's still time dependent. So in this limit, we just get this a linear equation in X, but it has a time dependent coefficient here. So this is a collection of harmonic oscillators, and the frequency is time dependent. So another general property is that in a vacuum solution, the trace of A is actually 0. So what that means is that there are some eigenvalues of A that are positive and some are negative. And we can see that the positive ones actually lead to unstable modes in this equation. And so that would be a mode that expands. Great. So now let's move on to strings. So this was first analyzed by Horwitz and Steiff. So the analysis is almost the same, except now we have an infinite number of harmonic oscillators, not just one, and they're labeled by this mode number n. And the frequency is given by this coefficient here that depends on n. So there are a couple of approximations that I'll have to use in different regimes of this problem. The first is called the shockwave approximation. So this holds if this frequency is actually localized in a small range of tau. In this case, I can just approximate it by a delta function. And in fact, this will be the case at very early times at the beginning of the blue line in the picture before. And so this is the differential equations are then similar to strings in a shockwave, so I'll call it the shockwave approximation. The second approximation is if the frequency is approximately constant in time. If this is true, then we can apply the adiabatic approximation. And in fact, this will be the case at very late times. Also, note that if an eigenvalue is very large and positive, then we have many unstable modes because the mode is unstable as long as the frequency is positive. And if this eigenvalue is positive, then there are many n for which that's the case. And so that will lead to a lot more instability than for a point particle. So now I'll specialize to an ADS5 black hole. In this case, because of the rotational symmetry, this matrix is actually diagonal, and it falls off like 1 over r to the 6th. A2 and A3 are along the sphere, and A1 is along a combination of the radial, the time, and the phi directions. So to see what we expect, suppose we start with a circular string that's coming in near the null geodesic, so it starts out as a circle. Well, it's going to be tidally disrupted by the curvature of the black hole. So in the radial direction, it'll be stretched out a bit, and in the spherical direction, it'll contract. Yeah, so that's what we expect for the analysis. And note that this is traceless, as I said it would be. Okay, great. Any questions about the Penrose limit? Okay, so now let's study the problem of the singularity resolution in string theory. So I'm interested in the behavior of the boundary two-point function. In this first case, near t and phi equals pi pi. So I'll just remind you of the kinematics. So we're interested in very close to the beginning of this blue line. So I'll call that the early time limit. And that's the limit where the geodesics are very far away from the black hole. So in this talk, I'll actually compute a slightly simpler quantity, which is the bulk-to-bulk propagator, very close to the light cone, and I'll show that the singularity is resolved in the bulk-to-bulk propagator. So that's slightly different from the boundary-to-boundary propagator, but the physics is in fact the same. So you might say that this bulk-to-bulk propagator is not a well-defined thing in string theory, but in fact it is, because it's the path integral with two d-instanton boundary states that are placed at the endpoints of the at the 2 points in the correlation function. So that's at x final and x initial. And so this is the world sheet path integral. It's the zero mode correlation function, G0, and then there's some fluctuation determinants. And these are the determinants for all the modes from n equals 1 to infinity, and for all the coordinates a equals 1 to 3. And this is just the frequency here. And this determinant is specified according to these boundary conditions in the path integral. So if you want to be completely precise, you can actually compute these things using the Gelfand-Yaglom theorem. But I want to be more sketchy, and I'll just compute the magnitude of these determinants. And this will allow us to bound the propagator on the light cone. So the reason the magnitude is simpler than the phase is because there's a simple interpretation in terms of particle production. So we have some time-dependent harmonic oscillators, and in this time-dependent case, the in vacuum is not going to be the same as the out vacuum. There's going to be some particles in the final state, and the overlap of the in and the out state is given by exactly this this inverse determinant if we take the magnitude here. So this is what I'll compute this overlap here. So now let's compute this thing. This is the form of the plane wave matrix. We see that a very large PV, so a very large momentum, this thing becomes a delta function in tau. So it's concentrated mainly around tau equals 0, and so we can use the shockwave approximation in which this thing is a delta function. the equations of motion, for example, for x1, then take this form, and they say that the field x1 just gets a discontinuity at the origin, and the discontinuity is given by something proportional to p, so it's very large at large p. So to solve this, you just make this ansatz, free fields away from the origin, and you find the Bol-Lyubov transformation, which is given here. And so now you can just compute this overlap, and you find this form. So we see that at large p, this overlap is very small for small n. So that means that many particles are produced in the final state, and so the overlap is small, and that will be the origin of the physics of the singularity resolution here. So that's one of the determinants here, and now we just multiply them all together, and we get a simple form here. So we see that this thing is exponentially small at large p, and the reason, as I said before, is because there are many modes that have a small overlap with the vacuum here, and multiplying them all together gives an exponential suppression at large p. So that gives the determinants in this formula, and now we just need to plug in the zero mode here, G0. But that's easy because we can just Fourier transform the ordinary propagator, and what you find is that G0 is proportional to square root of p. P is the momentum. So another way to say this is that if we didn't include the stringy contributions, then the propagator would be singular on light cone, because this integral over p diverges at large p. Because the zero mode propagator is square root of p, and the integral of square root of p is infinity. But if we're interested in string theory, we should include these stringy modes, and I just plug these in here, and we find that the propagator is bounded by this quantity. And as I said before, the integrand is actually exponentially suppressed at large p. So this tells us that the answer is finite on the light cone, and the light cone singularity is resolved. So the interpretation is that at very large p, many stringy modes are produced. So the probability that a particle is just going to remain localized on the light cone is very small, and that leads to the resolution of the light cone singularity in this problem. So that's the basic mechanism. Are there any questions about this analysis here? Okay, great. So that was the early time limit, and so going back to this picture, that was near here, near phi equals pi and t equals pi, and now we want to go out towards the end of the blue line, where the photon is going to wrap the photon sphere many times. So that's the opposite limit. And we want to see if the singularity is also resolved there. So this case is actually easier. The geodesic is approximately circular for a long time, so we can apply the WQB approximation. And in fact, the frequency is constant near the photon sphere. And so the frequencies are given here. And for all n such that this is negative, the mode is unstable. So at very large p, there are many n such that this equation is satisfied. And so there are many unstable modes. And the number of unstable modes is given by n max is PV. So to compute the number of the produced particles, we just use this equation for the WKB approximation, and the number is given by this quantity here, e to the twice the integral of the frequency. And what you find is that the expectation value of the number operator is given by this, and this is very large because R plus is very close to our photon sphere. And finally, we just multiply all these expectation values together to find the overlap of the in and the out state. And what you find is that it's again exponentially suppressed at very large p. The coefficient of the exponential suppression is slightly different, but it's still exponentially suppressed. And so therefore, we just use the exact same argument, plug into the integral over PV. At large PV, this thing is exponentially small, and so the integral converges, and so therefore it is not divergent on the light cone. So the argument is very similar in this kinetic regime also. So to summarize, the singularity is actually resolved in string theory if we take a finite string coupling. Sorry, a finite string scale. I keep confusing string coupling with string scale, but yeah, here alpha prime is finite. Are there any questions about this? Okay. So now we can move on to more general black holes. So we can study Kerr black holes also. In fact, this is not an optimal situation because in ADS-CFT you can't have an arbitrarily fast rotating black hole because at some rotation parameter it becomes unstable. But we can study this at small rotation parameter. So in the case of equatorial geodesics, we have two photon spheres. One is for photons that rotate with the black hole, and one is for photons that rotate against the black hole. And in flat space-time, for extremal rotation parameter, the prograde photon sphere is actually on the horizon. So in 4 dimensions, this is what the matrix looks like. This is in ADS. So now there's 2 components because there's 2 transverse directions. And we see that the only difference from before is that L is replaced by L minus A times E. Here A is the rotation parameter. For non-equatorial geodesics, what you find is that the matrix is no longer diagonal. And so the oscillators actually mix with each other. So here's a picture of the singularities in this rotating case. And the main difference from before is that there's an asymmetry between the geodesics that rotate positive phi direction and the negative phi direction, and the slopes of these lines at very large phi are given by the velocities of the two photon spheres in the equatorial plane. So that explains the asymmetry here. So that was the situation for ADS black holes, because the question was motivated by singularities in the boundary conformal field theory, but in fact we can also study the asymptotically flat case. So in this situation, we can take the sphere at very large r and take 2 points on the sphere, and this quantity is probably not well defined in real quantum gravity, but we can still compute the 2-point function in effective field theory. And if you do this, you find that that everything is basically the same, except that there's no boundary, and so geodesics cannot bounce out the boundary. So there's only one branch to the singularity, and that's drawn here. So here, again, phi is the angular coordinate, and we see that the same basic behavior of this singularity. It approaches a straight line at very large phi. And again, what you find is that the singularity is resolved by string theory. So if we were somehow able to measure the 2-point function on the light cone in an asymptotically flat black hole, and you were able to show that it was infinite, then that would mean that there are no strings in the universe. Of course, we don't really measure these things in real experiments, so it's kind of just a thought experiment. But I thought it was interesting that this is a sharp criterion for stringy behavior near a black hole. Okay, great. Yeah, so let me summarize. I'm a bit early, but I'll conclude. So,
okay,
yep.
Sorry. Could you go back one slide? But here, in the previous case, in the ADS-CFT case, you expected to find the singularity at infinite coupling, because this became like a null correlation function on the boundary theory, right? But in the asymptotically flat case, do you have this? You don't have this dual expectation of what this should be, right? So that's what you meant by measuring this sort of experimentally?
Well, so let me clarify two things first. So first of all, in the ADS-CFT case, there's no reason to expect these singularities from the dual perspective. It's only from the bulk perspective, and in fact, they go away at finite coupling. So I don't think there's an a priori reason to expect these new singularities from the boundary. Now, in the asymptotically flat case, what I meant was that I don't know a way to actually measure the correlation function near a black hole. So I don't know whether this is a good experimental criterion for string theory near a black hole, but it's certainly a thought experiment that you can think about. Yeah, I'm not sure I understood.
No, yeah. I see. No, it's still cool. Okay.
Okay, great.
Thanks.
Okay, so let me summarize. So I wanted to understand the singularities of the thermal 2-point function. I first derived these singularities in the holographic setting, and then I showed how they were resolved at finite coupling. And this suggests that in the more general case, case of a conformal field theory at some finite coupling and finite, and that the only singularity is on the boundary light cone. So if I had to guess, that's what I would say. So there's a couple interesting things that you can think about as a further direction. So here I only talked about the one-sided case. As I mentioned before, the two-sided correlators is a lot more complicated. In fact, there's a similar singularity in the two-sided correlator, and the corresponding geodesic gets very close to the black hole singularity. So that's a really interesting situation where you could probe, possibly probe the physics of the singularity, of the black hole singularity, by studying this singularity in the two-point function. So one thing we're trying to understand is if this singularity is actually resolved in string theory, or if you need to study really the physics of the black hole singularity to understand it. So another question would be, in the case of extremal curved black holes, in an asymptotically flat case, there's this analysis of Bagnado's Silicon West, and what they showed is that the black hole effectively acts as a particle accelerator. So if you shoot two particles in from infinity, then they actually collide at very high energies near the horizon. So that's unique to extremal curved black holes, and we want to understand. We're trying to understand if you could actually see this in the bulk point singularity, if there's some signature of this high energy effect in the correlation function. So that would be a couple of future directions, and I'll conclude there, and I'll stop for questions. Thank you.
Okay, thanks, Matthew, very much. We already had some questions, but we have time for a couple more.
So I have a question about the earlier part of your talk, where you were invoking the geodesic approximation.
Yeah.
And I'm just wondering if this is a controllable approximation in this case of real-time.
Yes.
Because like the way it was born in the Euclidean signature, where, I mean, like it makes sense, but this is Lorentzian, so.
Yeah. You have to do this annoying analytic continuation, but yeah, in the end, this is a good approximation. One thing you can do is to approach the singularity in not along a space-like direction, but along the complex direction. And in that case, this is really a controlled approximation to the correlation function. So I was a little bit cavalier with that, but yeah.
Do you do this in the paper actually?
Yeah, we do it in one of the sections, and we need to do that to compute the boundary-to-boundary correlator.
Okay. Yeah.
But basically, this is the analytic continuation of the real thing that one should do. But yeah, that's a good question.
Thanks.
All right, well, if there's no further questions, we thank Matthew again.